through some relatively painful derivations, we got to this solution, which is Mitchell solution. And I told you that it's good that we have a lot of terms, because depending on the physics of the problem that we are considering, then you can choose certain terms and build a solution for that particular problem. And we have started looking at axisymmetric problem. Does anyone want to explain what an axisymmetric problem is in general? When we say an axisymmetric problem, what type of a problem it is?
Axis independent. Sends them across. Doesn't change the angle. Doesn't change the angle.
Exactly. This is exactly what I wanted to hear. So if we go back, and this is what we want to do often. So if you have written something up, put a note for this page where Mitchell's solution is, because we are going to look back at this often. If you look at the solution, there are terms which are which have theta in them, right? I've forgotten to make all thetas red here. So you see there are terms where theta is in them. When we have an axisymmetric problem, the definition is that doesn't matter where you are looking, so the solution has to be independent of theta. So when I'm saying we need to look at the physics of the problem, that's what I mean. Another point to make is that when you are thinking about axisymmetric problem in elasticity, what has to be axisymmetric? Is it enough that the geometry is axisymmetric? No. The loading, what else can be axisymmetric? The loading has to be axisymmetric. How about the material? I mean, this is linear elasticity. Everything is isotropic and homogeneous. But generally speaking, if you want to have an axisymmetric problem, you have to have isotropy, right? You cannot have direction dependence in geometry, in loading, in material properties, etc. Now, with that, we go and take this piece of, because if you want to exclude everything which has dependence on theta, you are left with the first line. And then we looked at this first line for the stress potential. That's what it is. And then the relationship between a stress and a stress potential are given. You can see them. And here are what you would get if you plug in this stress potential. So this is where we are stopped. So I'm going to continue right from here. Any questions so far? So without showing everything, like just looking at just certain parameters that we need to develop the solutions later on. So if we consider plane stress solution, we can obtain the strain solution, and then from a strain you can get the displacement solution. And I skipped the strain. You can look in the book. We are in chapter 8. So Mike, we just started basically reviewing what we did last time, and then we are just going from a stress to displacement. So I'm not writing the strain solution for you, but I'll write the displacement solution because we are going to use it later. So we have UR and U theta, and UR for the axisymmetric You know what? Let me add here axisymmetric because this will be a new, and I'm writing in the wrong page. Good that I'll check. So axisymmetric solution continued. And then I jump into where I was before. So plane stress, solution, so just a displacement solution basically. U sub r is 1 over e minus 1 plus nu over nu a1 plus 2 1 minus nu a3 r log r. And last time I told you that log r in this class is natural logarithm. It doesn't imply basis, a base of 10 by any means. Let me check. So we have the three constants. Let me see, there is an error. This is 1 plus, everything is good. And then plus a sine theta plus b cosine theta. And then we have u theta, which is 4 r theta over e a cosine theta minus b sine theta plus cr. Anything odd here? So you see that also I started with a stress potential which had no dependence on theta because of the you know, when you go from a stress to a strain, things are kind of clear in linear elasticity. When you integrate, go from a strain to displacement, things can go wrong. As you remember, for example, in plane stress, somewhat displacement became dependent on z. So this can happen, and this is what you see here. But again, depending on the problem, as you will see a little bit later, then we can decide what terms to keep and what terms not to keep. There is another part. Before, when we developed displacement solutions, what did we have in all the solutions? We had constants, which were representative of what? We had something in displacement solution. It was a little bit special in the sense that it is not unique. Remember, when you think about the general solution to a boundary value problem in elasticity, it is unique to what end?
So the boundary conditions.
No. The general solution. We are going in the right direction. I don't know who was first, Prabha or Zach.
Infinitesimal rotation.
Infinitesimal rotation. So here you have exactly the same thing. It just looks a little bit different from in Cartesian. Given that in polar coordinate everything looks a little bit complicated, right? And it's because we are not used to it as much, we may not see it necessarily. So, and that's why I've written this thing like that. So these terms with A, B, and C, these are again those infinitesimal rigid body displacement. Which is a combination of a rigid body rotation and translation. And of course, you see that here there is a term where theta appears explicitly. So that's something to think about, because if this is the case, then if you have a physical problem where you have multiplicity, where you can't have multiplicity, remember? Then you can't really use this solution. And the way to do it is just to say A3 is equal to 0. So you kind of try to tune the general solution to your specific problem. We will see the example in a moment. What else I wanted to see here? Now, how do we find A, B, and C, the uppercase? So make parallels between what you've learned in Cartesian coordinates and polar. It's the same. What we did there. Let's first start with A1, A2, A3. To get those, what do we do? Boundary conditions. Now for A, B, and C, what do we need for that? Fixity conditions. Okay, so to find them, we need to apply and one common way to do this is to say that just that your structure, that your domain is not rotating, so you just fix it. So it's just fixed. It cannot rotate around the center, which would be the axis of rotation, right? Everything is 2D. So if we do that, all of them will be 0. So I'll just write this down and kind of forget about them. So one common fixity condition is to constrain rotation about the origin. So then you will get all of them equal to 0. Okay, so I talked to you about theta. So let's just jump into the example. That would be the fun part, to actually apply this to solve a problem. And here is the example, the first example that we consider. So it's a thick walled cylinder under uniform pressure. So when I draw the geometry, and I know that there is a way to actually draw circles here, but I'm not very good in that. So let me just try to okay, it's not too bad. Well, these are concentric circles. Okay, that's the best I can do. And you have seen, so that's why you've been seeing this in different homework problems, because we kind of knew that I knew that we are going to need this here. So we have, this is the cross section, and then we have the inner radius and the outer radius. And then the pressure, I don't draw all of the pressure. So the outer pressure is P outer, and then the inner pressure or maybe I should write this down too. PI inner uniform pressure. So, do we expect any kind of multi-valuedness here? First of all, is this an axisymmetric problem? Is the geometry axisymmetric? Is the loading axisymmetric? No? I didn't draw the whole thing, Prabha. Do you expect me to put all the arrows? I mean, please. But yes, so that was a good point. If this is all the loading on the structure, no. But just accept that, imagine. Exactly. So that's why I wrote it down, actually. Don't worry about it. So it is axisymmetric. Now, do we expect here any kind of multi-valuedness? And by multi-valuedness, what do I mean? At every point, do you expect to have different values for displacement? What example did I give last time where we could have a potential multi-valued displacement? a crack, right? Some of you were not here last time, so I told you that if you have a crack, right, in mathematically you just model the crack with one line. And you allow the displacement to be discontinuous, meaning that you can have a value for displacement basically at the same point two values, one which is just below the crack and the other which is just above the crack. But since it's only a one line, it is as if at one point you have two different displacements. So your displacement field won't be continuous anymore at the crack interface. So this is an example. Do you have any reason to believe that here you have multivaluedness? What does it tell you in terms of the Mitchell solution? What constant can be set to 0? Go back, look at the Mitchell solution, tell me. Probably it's okay to be right or wrong, so I don't hear when your answers half of the times.
Yeah, you're not scared to be wrong.
That's fine, but he tries. But he tries, right? What should I set to 0 if we are sure that there is no multivaluedness? Theta. Can we put? So that's a good point. So you see, it's important that we ask these questions. Can we set theta equal to 0? It's like saying, so going back, it's like saying put x equal to 0. For this problem, theta can be 0 to 2 pi, right? It's the whole thing. To this domain, right? It's we have r and theta, so theta can be anything. The solution cannot depend on theta. These are two different things. Is this?
You're specifying, you can't say theta is a number, but you can set the constants associated with theta equal to 0.
Right.
Yeah.
So the solution cannot depend on theta. But if we say theta equal to 0, it means that you are just considering a line. Mm-hmm. I just want to make things clear here. Mm-hmm. That was good. So which constant? A3. So now please look back and see what you would get for sigma RR, sigma theta theta, and sigma R theta. I've written down the equations before last time. How would they look like? At the end of the class last time, I wrote you okay, so I hope I can show you that. Just want to make sure that you are with me and you are not. So this is how they look like. So Cody, here are, okay, you found. You prefer your phone screen to this big here? Okay. So if you have the expressions, you should know what comes next. So I write it down quickly. I don't know why, but I've used uppercase but I think I know why. So I'm just using uppercase A2 for 2 times A2 because it doesn't matter if you have a constant, if it is 2 times of that. So it's fine if you don't have it written that way. So then we only have 2 constants, right? Does it make sense for sigma r theta to be 0? Yes, right? It's like if it is axisymmetric, which direction does it go? So it's 0. Now boundary conditions. This is something we have practiced a lot. So write the boundary conditions for this problem. You should be able to do that really fast. Now that I finally graded everyone's homework number 5, when we say boundary conditions, they have to be expressed in terms of displacement or in terms of other terms. Because our formulations are either in terms of stress or displacement. So you cannot just write fraction is equal to this. This is not boundary conditions. This is useful to solve an elasticity problem. And this problem you have seen a few times already. So I write it, I make the screen blank because I want everyone to write this once. How many boundary conditions do we need? 2. Okay, so the reason I wanted to write this down explicitly is because almost half of the class, or maybe more, you have made a mistake in the signs when in the homework problem. So here, you have to always remember that the normal is outward from the surface. So if the surface is inside, it is like that. If it is outside, it's like that. Okay. Everyone has that negative sign there. Okay, so for the outer one, it's negative because the traction is in the negative ER direction. So that. So now we have 2 constants, A1, A2, 2 boundary conditions. So trust me that if you put these things together, you are going to get A1, A2. I don't subject you to that. So I just give you how things will look like. But it's a straightforward. And the forms of these equations are important. So because we are going to look at then the extreme cases, limiting cases of them. So it's important that we write them down. So after applying, let me put some numbers here just to make things more. So this is boundary condition number 1, boundary condition number 2, we calculate A1, A2, and we find the stresses. So sigma RR is RI squared P naught minus Pi over 1 minus R sub I over R naught squared 1 over R squared, okay, plus R I over R naught squared Pi minus P naught, and this divided by similarly to the other term. This presentation looks a little bit different from what you see in the book, but it's essentially the same thing. The book is using R1 and R2. We are using RI and RO because it's easier to remember what is what. And then there are some other, but if you multiply things, the both solutions are the same. And then sigma theta theta, it is negative Ri squared P naught minus Pi 1 minus Ri over R naught squared plus is pi again minus p naught. 1 minus ri over r naught squared. So this is the solution for the thick wall pipe that you saw. Now let's consider a particular solution just to a little bit to understand the character of the solution, what it actually means. So let's consider one particular case. So consider the case with internal pressure only. So where you have Pi equal to P and then P naught 0. And for a particular geometry where the radius of the inner pipe is half of the outer. So, and then we can plot the dimensionless stress. So if I the numbers don't matter here much, more the character, so I consider bringing you the solution, but it's more like how it looks like. So if you look at how the solution would look like through the thickness of the this pipe, what did I call it? Cylinder. So I have R over R naught, that's dimensionless radius, and then if I look at the dimensionless stress, sigma over P, it looks like that some numbers here and use some nice colors. So sigma R, it basically starts from negative P and goes to 0. So it makes sense. If you don't have any pressure on the outer surface, the stresses have to become 0. Then you have traction free. And then it starts from negative P from inside. Sigma theta theta starts with a value which is 5 over 3, and it kind of goes towards 1. So what is the moral of the story? Where does the worst, so let's see, if you want to check a pipe like that for failure, where is more critical? Where things, where stresses are the largest? Yeah, the interior part, which makes sense because that's where you have the pressure. But you see that the hoop stress, it actually, it is always positive, so it never goes towards 0. But the radial stress is going. So this is one particular solution. In in elementary classes, you should have seen thin-walled cylinder solutions at some point. So if you take this solution, you can actually go and get the thin-walled solution. But what is more interesting for us is going back to what I told you before, to try to see what are the limiting cases of this problem. For example, what happens if I let the outer radius to become very, very large? So think about this problem. I should show you the geometry, because I want you to think, not just to follow step by step what I'm doing, because that's not the point here. Now this is the geometry. Now if I let R0 become very large, what type of problem am I looking at? I'm sorry. So Prava, a rule. From now on, I have to hear what you are saying, because whether it is right or wrong, most of the time it's right, because you are a good student. But if I don't hear, I may as well not even know that you said something, right? So, you want a second chance? No? So I'm just asking you to use your imagination. How much is it left at this hour of the day? To tell me, if I take R0 and I let it to be very, very large. I'm sorry? That really scares me, because plane strain is not about geometry, is it? Somehow, you're right. But if everything is in a plane, right? Now I understand why you both said plane strain. So yeah, okay. It's something about geometry, but here that's not the kind of geometry. The geometry of plane strain is in the direction perpendicular to the wall. Right? So if this was an infinitely long pipe, then it was plane strain, no matter how large the R0 is. So just to make sure. Guys, please tell me. So if I let the R0 become very large, it becomes like, why would it become a crack? A full cylinder? Let's say R0 is very, very large. So you're getting there. You're getting there. So if you have, do you remember I told you something about the Warhol Bridge in Pittsburgh? Most of you haven't seen for some reason. If you have a situation like that, right? Now, that is very finite. But if you want to study what is happening around a hole, right? If you zoom in, you don't see much from the domain, right? So if you let the R0 becomes very, very large, it becomes a problem of a plate, of an infinite domain with a hole in it. So I have the solution for this case, but I can let R0 go towards infinity and get the solution for an infinite domain with a pressurized hole in it. I'm talking about, I can say, okay, P0 is 0. I have the solution for any P0. P0 is 0. I have Pi. I have some pressure inside the hole. I let R0 go towards infinity to get the solution of an infinite domain with a pressurized hole in it. Gerald, you don't see it?
If you have a different
Let's see if it matters. Yeah, exactly. That's a good point. Let's see what happens. If it is really, really big, does it matter or not? And the way I say it, it's obvious if it matters or not, but okay. So, assume that P naught is 0 and R naught is becoming very large. Then this solution applies to an infinite plate with a pressurized cylindrical hole. So if you do that, you get for sigma r negative pi ri squared over r squared, and then sigma theta theta is pi and u r, so this is a stress solution. And I draw it here, so this is like that, and then here you have a hole of radius Ri, what conditions should we have to be able to do that? No. So this is a solution for a linear elastic problem, and then you have that, and you have the same solution for another hole which is also linear elastic everything. Then you can use superposition. So that's actually one way that you can use a solution like that and get the solution for a more complicated cases. If everything is linear elastic, if all our assumptions are valid for that particular case. What is R? It's just R. It's like, so in polar coordinates we have r and theta. So it's like that r, from coordinate. So that's the dependence on the distance from the origin of the hole.
So if we're approximating a 3D problem using this, where do we insert the plane across or the pattern across the plane? Say, should this hole be cylindrical or can it be spherical?
So in the beginning we assumed that it was cylindrical and we assumed the plane stress solution. So that you can, basically you can assume, if it was a very long one, you can assume it's plane strain and then you can use plane strain.
But it wouldn't work if it was spherical.
No. Then it's not 2D anymore. Then you cannot use a 2D formulation. If it is a spherical, then you can work in the spherical coordinate system and develop a solution. But this solution will not be applicable there. Does it make sense? Because I'm using the stress-strain relationship from plane stress, so that won't be applicable to a case like that. Now things become more interesting. First of all, tell me if you can think about any kind of application where this could be useful remotely.
But in terms of heat, use for heat dissipation from heat source. But since this is pressure,
So for heat, you have to solve diffusion equation, right? And then you find out how it's going to be spreading. This is different. But I'm thinking about, if you can think about a physical problem where something like that could be useful.
pipes bursting from source.
Submerged pipes?
Yeah, like something that's deep in the ground. It has to be deep enough that it's away from, if you consider, but there sometimes that pipe that's deep in the ground.
Yeah, I did think that's right. I didn't think about it, but you can actually use it for that. You guys, when you hear the word infinite, I think you really think really long infinite. Now, sometimes this is just an approximation. It is like the boundary is far enough, and I told you that how the effect of boundary would change from the boundary. It's exponential. So when you think infinite in this sense, think about this be far enough, right? And far enough, we saw that it's exponentially decreasing.
And the direction of the pressure has to be greater all along that line. In practice, it's very difficult. You need to have source where the pressure goes all the way down.
Are you talking about the boundary conditions?
Yeah, the canal pressure. It has to go on radial axis or symmetry.
But typically, pressurized, like for example a pipe, typically it would be really like that, right?
After a while.
Yeah, so this is a good point. Look at the stress solution. In the denominator you have r squared. So when r is increasing, it's going to go away. And that's why I was showing you, right? The effect is going to go away. So it's going to be a smaller. That's given. Yeah. Yeah. I don't really understand. So could you? Riveted joints, yeah, that's a good example, because I talked about the bridge. I kind of want to go back, and if you have a truss, look at this bridge in Pittsburgh next time. So you have all these bolts. So if in your imagination take the bolt out, it's applying some pressure, depending on where it is on the bridge. We don't want to go to those details. To the big girders, they're really huge. The yellow bridge in Pittsburgh. Please look at this bridge next time. So it could be approximated with that. But having said that, we are interested more on the other problem, where you have a plate and you have just a hole in it. So the plate is under stress, but you have a hole in it. can you think about a way to use the same solution for this problem? I want you to be the one telling me if I would be able to use the same problem for a plate with a hole in it, and under what conditions. So there is pressure inside the hole is 0. So let's be clear about that. Most of the time what you are very interested in is some pieces, some structure where you have a hole in it. And you want to see, for example, if that hole, how does it affect the stress? We talked about the stress concentration. So can you think about a way to use that solution for this problem? What do I do? Traction? What are the limiting conditions here? Let us all think for a few seconds. So you have this is the problem you solve, right? And I'm saying, okay, Pi is 0. How can I make this work here?
This has a finite.
Yeah.
So, but the solution you gave to us was supposed to be for approximately an infinity.
Think back at this solution.
This pair, you're going to use the boundary condition for this, so it's not going to work.
So Kingsley says that this is not going to work. That's one opinion. Yeah, I mean, you are thinking that there is no way to apply this to a problem like that.
Yeah, the one you gave us before was for an infinity domain. That's the boundary. You make a boundary. You're trying to be going to infinity.
No, let me make things clear. I took this solution, which I obtained for this case, with now I'm putting all the arrows there. I took this solution, which is here, as you can see, and I let P naught equal to 0, no outer pressure, and then I let R naught be infinite. And I took that solution, the very same solution, and I said this is the solution to this problem, because it looks like this problem. My question right now for you is those conditions which would make this solution work for this situation. It can work. How can it work? For what domain can it work? And how should I make this work?
The same way that for reciprocity theory, you place a load and cause displacement at the other location. When you place that load at that location, it causes the force displacement. So if what is changing only is the pressure going from inside or coming from outside, there is practically not so much answer.
I'm asking a simple question here. We didn't talk about energy methods, so we haven't talked about reciprocity. I'm just saying how to go from here to there. The reason I'm asking you this, and I want you to participate, is that a lot of times you read a paper or you find a solution, but your problem doesn't look exactly like that. So it's very important to kind of develop this imagination to try to say, okay, here is this solution, here are the assumptions. Think about the assumptions and see whether your particular experiment, your particular project, is this going to be applicable to that case. Arrows?
Yeah,
PI is 0. PI is 0. Yeah, I don't want to have any, because most of the time you have a hole where there is no pressure. If you ignore air pressure.
you have to go back to the original solution and solve it.
Yes. but what should I do to that solution? So again, here I set P not equal to 0 and I let R not go to infinity. My question is, what should I do for that solution to work here? Which radius? Why? This looks very infinite to me. Yeah, Gerald. I'm sorry. First, let me find out what John said. Yeah, but a P naught cannot be. If P naught is 0, there is no problem. Right? So we are getting there. Sorry, Kingsley, what did you say before? So I have to kind of go around.
I was saying in place of Pi, you use minus P2.
Yeah, you are going in the right direction, both of you. Gerald, did you want to say something? Why minus?
It's going back.
Okay, I mean, it can be plus or minus. So, what about R? What do I do with R? R naught still has to be going towards infinity, right? I'm not asking what would be the results, I'm just asking what would be the conditions, right? What are the conditions?
To clarify,
Yeah,
you're asking
I forgot
for
that.
for a plate with some kind of pressure on it.
Yeah, but I have to, exactly, so I have to have a pressure.
R has to be RO, the outer radius needs to be big enough that you can assume that a sphere is acting like it's in the infinity, and then to your supply, set the I equal to 0, and say whatever the far field tension is, and do something to the
That's, do you want to add something to that, Jerry?
So we took the last solution we found, we're trying to
Not the last one. That's why I draw this here, right?
So we're not using the solution above. So I thought we were using the solution we found to see whether something applies.
Well, I think I explained it because that's why it is here, right? I said,
the small one is going to be, or it's going to deform.
this is elasticity, so everything can deform. So maybe we stop here because I'll explain to you what it is. So my intention is that you can think, because I know that a lot of you took solid mechanics, but it looks like you have a lot of trouble applying area stress function that you learned there. So my intention is that, I hope that you take it seriously. So I don't do that to waste the class time, or So this is a little bit unsettling, I think. So the way to go from this problem, as it's very clearly shown to that, is you assume that Pi is equal to 0, and as Zach said, to be able to apply this to a plate, you have to have a very large plate that when you focus on the hole, it looks like you have constant pressure here, right? So to be able to do that, you need to have some sort of hydrostatics. You have to have some sort of a stress which is equal everywhere. Otherwise, this solution would not be applicable, because we have here PO, P naught, and this P naught is the same everywhere. So to make this solution work for that, I have to assume a situation like this. If you have a stress, let's say if you are stretching, applying a stress, we are in 2D, so imagine you have a two-dimensional set of a stress like that. If T is the same, if it is the same stress, if you, now this, you're applying this to something large. If you go close to the hole and look at it, it looks like you are actually applying a uniform pressure. So you can use exactly the same formulation for that problem. Also, the problem looks very different. So that's the whole point. Sometimes the problems, the solutions are for some problems which look different. But if you think hard, sometimes you can use them for the problem that you have in hand. So if you do that, so R naught is going, then, so if we call this T, so what Kingsley was saying earlier is correct. So if we consider tension, here P naught would be negative T and Pi would be equal to 0. So it would be exactly the same problem as before. And if you apply that, then you can obtain expressions for sigma RR and at inner surface so if you can see that at inner surface sigma RR will be equal to 0, and sigma theta theta, you can very easily see if you substitute R for Ri, would be 2 times T. So meaning that if you have a hole inside the plate where the traction is T, what is happening to sigma theta theta? If you look at sigma theta theta, it's a component which looks like that, right? For example, it is 2 times the traction that you are applying. So how much is the stress concentration factor? 2. So you see that putting, even in a very large plate, inserting a hole, you will have double amount of stress at the inner surface of that particular hole. So answering your earlier question, it matters. Even if the plate is very large, if you apply the stress, you're going to have double amount of stress at the inner surface of the plate. So let's stop here and then we look at some other problems next time.